Hello students. We've been talking about vector spaces for a while, and then more recently maps between vector spaces. Now in this class or video, we're going to be talking about a very special subspace associated with a linear map between vector spaces. And this is called the null space. And let's write down exactly what that is to start off. So let T be some linear map. Yeah, let's call it T. I don't really care which letter. You could use a letter of your choosing. So let T be a linear transformation. Transformation's a long word, but when you use the words linear transformation, there's an implication that V and W are vector spaces. I mean, of course, they're vector spaces here, but you could say let V and W be vector spaces and T be a linear map. Lots of ways of saying this so far. Okay, so let T be a linear transformation. We define the null space of T, which is going to be written null T, to be, it's a little redundant for me to write that there, but I felt like it, so the set of all V in V so that T sends V to 0. So everything that goes to 0 is the null space, okay, by this transformation. So, I mean, maybe let's look at a few examples just to start off. Let's make one up. Let's make a few up. So let's pick a linear transformation. I'm going to say T is going to be a map from R2 to R. Nice little map. What's T going to do? T of x, y is going to add them. So basically, I take in two real numbers and I output real numbers. So R squared is a vector space, R is a vector space, it's a map between vector spaces. Is this linear? Well, let's just, I guess, check quickly. Oh, by the way, I should do a double parentheses here because this is T of the tuple, the two-tuple xy inside the function. Just to be rigorous, not to abuse my notation too much. So let's see what the null space of this transformation would actually be. But let's also show it's linear. So if I were to take T of xy plus, I don't know, uv. Well, I have to do this on the inside first. So this is going to be x plus u. No reason to write the u first, so I'll write x plus u, and then y plus v. Okay, so what's this equal to? By definition, this is equal to x plus u plus y plus v. But what do I want to get? Well, I want to get T of xy plus T of uv. I can group the x and y together. So this is equal to x plus y plus u plus v. Now, T of xy is going to be x plus y. So this is T of xy, and this is T of uv. So definitely behaves correctly with respect to addition. What about scalar multiplication? Well, T of lambda xy by definition is T of, because this is on the inside, it has to happen first, lambda x, lambda y. Now what does T do? It adds them. So let's do lambda x plus lambda y. Okay, so what is this equal to? Well, this happens to be equal to lambda of x plus y, which is lambda of T of x, y. So I didn't say we were proving it, but we just proved that T is linear. That's not the question. The question I want to ask is, what is the null space of T? it's important that I checked that it was linear if I didn't know. Though if I tell you a map is linear, I'm probably not trying to set you up to fail and say, ha ha, I lied, that map was not linear. So you don't have to prove something's linear if I'm telling you, this is a linear map, find the null space. But just so you know that. Okay, so now let's move on to the null space portion. So I want to know what the null space is. So what I want to do is I want to solve this equation over here. T of v equals 0. So here I'd want t of xy to be 0. So this is what I want to solve. So what does that mean? Well, this is the set x plus y equals 0 because this is equal to x plus y. So I have the set of all xy in V so that x plus y equals 0. However, I might want to write this a little differently. I know that if x plus y is 0, what does that mean? Well, that means that y happens to be equal to negative x. So this could be the set of all x comma negative x in V. Here I could say so that x is in the reals, but that's kind of obvious from R. I think that's an okay way of writing it. There's lots of different ways of writing. I could have taken the set of all negative x, x. I could have written it like this, the set of all negative x, x, so that x is in the reals. That's a nice way to write this as well. Maybe even nicer than that way, because it satisfies our normal set builder notation of having a so that in there. We found a null space. What do I know about this null space? Well, I actually already gave it away a little earlier. I claimed that this null space was in itself, I said I was going to talk about an exciting subspace. So them saying that this is in itself a subspace, which means this in itself is a vector space. So what vector space would that be? Well, let's try to make sure it is a vector space. I mean, in this situation, I'm taking the set of all x comma minus x so that x is in the reals. So this is a subset of R2, and I want to show that this is a vector space. Now, it's not empty because 0, 0 is in this. Let's give this a name. I'll just call this W for now. I could call it null t because we know W is equal to null t. But what do I know? I know 0 is in W, so W is not empty. And then I know if I have, let's say, A minus A plus B minus B, well, this is going to be what? It's going to be A plus B minus A minus B, which is equal to A plus B minus A plus B. So what can we see? Well, we see, hey, if you start off with two things in this form, x minus x, I get something of the form. So this is going to be closed under addition, but also scalars. If V is in W and lambda is in the field, then, well, we know V has to be equal to A minus A for some A. And then what do I know? Well, I know that lambda of, well, I'll write lambda V. I gave it a special name this time. Lambda V equals lambda A comma minus A, which is going to be lambda A minus lambda A. And this is of the form x minus x, just set x equal to lambda A. And I see that this is also in W. So this is in fact a subspace. And this is going to be a general thing. In general, we're just always going to get a subspace. Let's show that in another video.